Okay, so right before we took our break, we were talking about pointers a little bit, and then this concept of passing by value versus passing by address. So let's look at this as an example real quick, just to actually see Java perform its magic as a, let's see here. So I'm going to show you an example of passing by value. So I'm going to create a variable here, a method, static void change num. This guy's going to take an int as a parameter, and we're going to say int n is equal, we're going to say n is equal to 5. So whatever integer we pass in here, we're just going to change it to 5. All right? So that's all this method does, is it takes a number as a parameter and then overwrites that number with 5. All right? So I'm going to say int a is equal to 7. This is out in main. I'm going to say system.out.println a. What kind of method is this? Class method or instance method? How do you know? Static. How do we call class methods? Okay. Name of the class which the method was defined. So we're going to say driver dot change num, and we're going to pass in an a. And then we're going to print out a again. Okay, so print out a, call the method, a goes into the method right here, we change it to 5, then we print this out. What's the output of this program going to be?
7 and 5.
It's 7 and 7. All right, 7 and 7. This is an example of pass by value. Why? This guy is an integer primitive type. Java automatically treats integer primitive types as automatically treats all of our primitive types actually as pass by value. This is equivalent to what we were talking about earlier about me borrowing a quarter. You would hand me the actual quarter. Java notices that this guy right here is only 32 bits big. Okay? In a 32-bit operating system, a memory address is 32 bits. In a 64-bit operating system, a memory address is 64 bits. So if you have a 64-bit operating system, it's actually less expensive to pass the actual value than it is to pass the address to the value. Okay? Now, less expensive is kind of in the eye of the beholder, though. Let's say that I was passing let's say it was a 32-bit operating system. So the size of a memory address is 32 bits. And I'm going to pass a long here, which is 64 bits. So technically, it is more expensive now for me to pass the long value by value than it is to give you an address where to find it. The address is 32 bits big. The value itself is 64 bits big. Okay? Now Java's not going to look at it and say, oh, well, since it's more expensive to pass the value than the address, we'll pass this guy by address. Java does not do that. Java still passes this guy by value. Okay? Now, so it's not only about memory footprint. It's also about what makes sense. This is a silver dollar instead of a quarter. You wouldn't give me a map to go tell me where I could go find a silver dollar. You would still hand me the silver dollar. Okay? It's a little bit bigger chunk of metal, but it's still something that you would hand to me as opposed to give me a treasure map to go find. All right? So it makes sense for all of our primitive types to be passed by value. Therefore, Java makes that decision for us. Okay? All right, so that's why A started off at 7. We passed it in to change num. And what did change num get? It got a copy of A. A copy of it. We changed the copy, which had no impact on the original. Make sense? Okay. So that's an example of pass by value. Now, pass by address, I can't show you yet because we have to learn about arrays first. So I'll show you here in 20, 30 minutes, something like that. All right? Because right now, you don't know how to work with arrays. So I can't show you me passing an array, changing it, and having that change be permanent. So you'll see that in a few minutes.
Well, if we say A equals driver dot change number A, what will happen? Well, we'll want to change.
What do you want me to say this right here?
Say A equals drive dot on the third line. If you just put A equals.
I get what you're saying. You want me to say that?
Yeah.
What does this guy return?
But how do you make it integer? So
Well, okay, well that's different. So if I make this guy return an integer, and let's have him go ahead and take the int in, and then I say return n, yeah, a will now be 5.
So that's not valid then.
Well, but it had nothing to do with how it was passed. We passed a copy of a into this guy called n. All right? We changed the copy to 5. Then we returned the copy. So the copy comes firing out of here, and we caught it inside of our original variable. So we changed the variable, but we directly changed it, not indirectly changed it. So it had nothing to do with the fact that it was passed by value. All right. So let's look at arrays here. All right, so syntax for an array. Syntax is type followed by opening close square brackets, var name equals new type open square bracket what do I want to say this? Num vals close square bracket semicolon. So this is the generic syntax for defining an array. The type of value you want to hold, followed by an open and close square bracket. This defines it as I'm going to create an array of these guys. Then your variable name, just like any other variable name. Then your value. So we're always going to use the new keyword. We'll talk about that a lot today. Followed by the type, same type as over here. And then in the open and close square brackets over here, we put in how many values we want this array to be built to hold. Okay? So as an example, I can create an integer array, call it AR, and this guy could be a new integer array capable of holding 10 integers.
What's the difference between the first integer and the second? Why do you repeat it twice?
Well, this is the type of this variable. This is the value that gets stored in there. So this says that AR is a bucket capable of holding this kind of animal. It's holding an integer array. Now I'm going to actually put the animal in there. So the animal is constructed using this guy. And this guy says create enough memory to hold 10 of these guys, 10 ints. Okay, and you'll see that in my example here in a second. All right, so this is the generic syntax for creating an array. So, go ahead.
Is that array an object?
No. The best answer I can give you is no. An array is not an object. An array is a primitive type, but it technically has a little bit of magic beyond just holding a value. Okay, so in Java, it's somewhere in between.
Array is between the
Yeah.
exactly primitive and exactly object.
Yeah, somewhere. Yeah, it's not exactly either of them. It probably acts more like an object than like a primitive. I think that's fair. It acts more like an object. So similarly, I can create an array capable of holding characters. Maybe call this guy the chars. This guy can be a new char array capable of holding 100 characters. So here's two separate arrays. This one can hold 10 integers. This one can hold 100 characters. Make sense? So this is the generic syntax for creating arrays. Now, let's see what this guy, and actually just to keep myself sane, I'm going to change that to 5. Now this can hold 5 integers because I'm about to draw some pictures. You can use less boxes with 5 instead of 10. All right, so I'm going to copy that. We'll come into here. Oh, might as well just have typed it. Integer array AR is equal to new integer array 5. Something like that. All right. Now, this is what actually happens here. This is like going to Walmart or Target and buying a container that has 5 slots in it. And each of those slots is capable of holding a number. But when I first built it, there are no numbers in there. It's an empty container with 5 individual buckets, 5 individual slots. So what I end up getting out of this is something that might look like this. All right, a structure that looks like this. I'm going to steal this here real quick. We're going to change the color of these guys. These guys will be that. And that will look like that. All right. Now, arrays have a way of telling us how many buckets they are capable of holding. And that is something like this, ar.length. ar.length in this case will boil down to 5. All right? Just like strings. And first of all, notice that there is no open and close parentheses on this. It's just length, which actually means it's a field. Don't worry about that right now. For right now, the way you get the length of an array is like that. Name of the array, dot, the word length, no parentheses. It'll make more sense once I explain it, but for right now, that's how you get the length of an array. It's a little bit different than getting the length of a string, but functionally, they give you the same value. How many characters are in the string? How many elements is this array built to hold? All right? Arrays, just like strings, are indexed. Bucket 0, bucket 1, 2, 3, 4. So last legal bucket is the length minus 1, just like strings. Okay, so they're 0 indexed, just like strings. Now, we need to talk about this new keyword here. Very, very, very important. New keyword. Just like I've said this, the generic syntax for variables is the type, the variable name equals the value, right? Well, part of this value here is the new keyword. And I referred to this one other time when I first showed you strings. I said strings are kind of a bad example for a first object, even though they're very important. Strings are the only object that doesn't act like other objects. Okay, we'll see this in a little bit. Strings, all objects are passed by address except strings. Strings are actually passed by value. And we'll see it as an example. But strings are just the exception. Okay, in almost every case. Defining a string, defining any other object uses the new keyword. Strings, not required. Okay, because they're such an important part of the language that they've given us what I usually refer to as syntactic sugar for defining strings. If I'm going to define a string, I can just say string s is equal to hello. I don't have to say string s2 is equal to new string hello. Both of these guys essentially do the same thing. And I say essentially because there actually is a difference. We'll probably talk about it today, but there is a difference between these two. All right, but in any case, this is syntactic sugar for this. It's shorthand. Okay, I just like syntactic sugar because it sounds cool. All right. So in any case, variables are always type, name, value. Part of the value for arrays is this new keyword. The new keyword I refer to as being our real estate agent. So the new keyword's like a real estate agent. So in real life, if you were looking for a house, you would hire a real estate agent, right? And let's say you were building a house. The real estate agent's going to go out and it's going to find you a plot of land for you to buy so that you can build your house on that plot of land. So the job of the real estate agent is to identify appropriate plots of land that will fit the house that you intend to build. So if you're going to build a 3,000 square foot ranch home, you'll give that to the real estate agent. The real estate agent will then go look for available plots of land in the area that you're interested in buying that have enough acreage to hold a house that meets your requirements, right? Okay, and the real estate agent's going to come back to you, and of course, she's going to do what? She's going to hand you the plot of land, right? No, she gives us the address where we can go look at it. She says, here's the address, go check out this land and let me know if this is in an area you're interested in, right? Okay, so the real estate agent ultimately takes your instructions, goes out and brings back an address that is a plot of land big enough to build what you're interested in building. That's what the new keyword does. We tell it what we want to build, it goes out and finds enough memory for us to build it and comes back with the address in memory where we can go and actually build it. Okay? New keyword's the real estate agent. It returns, well here, let's actually do it this way. It always returns a memory address. Okay? Which is actually another interesting thing related to what we talked about earlier. That means whatever's on the left-hand side of the assignment operator, when the new keyword is involved, will hold a memory address, right? So by definition, that guy is a what? He's a pointer. Pointers hold memory addresses. This guy always returns a memory address. See, I actually put always in all uppercase. That's like really always. It always returns a memory address. So since that guy always returns a memory address, whatever value, whatever variable then we're storing it in will hold a memory address. That's a pointer. Not that they exist or anything. All right. So new keywords are real estate agent. It goes out and finds us a plot of land big enough to hold whatever we're building. Okay. That's what the new keyword does. Finds us enough memory and always returns an address to the memory it found. Make sense? All right. So right here, the new keyword is going to go out and find us some memory. How much memory? Enough to hold that many of those guys. How big is an int in Java? How much does an int weigh in Java? 32 bits. 4 bytes, 32 bits. So how much memory do we need to hold 5 of those? 160 bits, 20 bytes, right? Okay. So the new keyword is going to go out and it's going to find a plot of land big enough to hold 5 integers. That means it needs to find 160 bits or 20 bytes of contiguous memory. Memory in a row. Okay? Because in real life, if you're building a house, you're not going to build part of your house in one piece of land and another part of your house on another piece of land. You need to find one piece of land big enough to hold the whole house. Right? I mean, that's how real life works. We need enough space to build my entire 3,000 square foot ranch. We can't build half of it on one plot of land and the other half on another plot of land and say that's a home. Okay? One big plot of land is what I need. Okay, so the new keyword in this case, the new keyword returns us a memory address that was big enough to hold this guy right here. Okay? And I say in this case, for right now, you can assume that's what the new keyword always does. When we start writing our own objects where we use the new keyword, it gets a little bit more complicated than that. But for right now, let's just say the new keyword always gets us contiguous memory big enough to hold whatever this is. Okay? So in this exact example, the new keyword will go out and find us 20 bytes of contiguous memory. All right? To make the math easy, let's say the new keyword came back. So we have AR. AR is right here. And AR is a variable. And the value AR is going to hold is whatever gets returned by the new keyword. And what is always the type of value returned by the new keyword? It's a memory address. Always a memory address. New keyword always returns a memory address. So that means AR will hold a memory address, not an array, a memory address. So to make life easy, we're going to say this is memory address 100. Okay? That's memory address 100. So AR is a pointer, which holds the memory address where we can actually find our array in memory. Okay? So I'm going to write some other things in here. Oh, sorry. You got this. So that's 100, 102, 104, 106. I know. 108. Okay. See, magic. I do magic up here. So, in any case, it's going to return for us the pointer where we can find this array in memory. And remember, I said that arrays need to be stored in contiguous memory. And why are these guys called pointers? Well, I'll show you. They're called pointers because they point. The value in this guy points to a real place in memory. That makes sense? AR is a variable that holds a value. The value it holds is the memory address. If I follow the pointer to that actual memory address, I find an array there. Just like if you handed me the piece of paper that had your address on it for your party, and I followed my GPS to your house, I'd find, my guess is not that hopping up a party. You throw good parties?
Yeah.
No, he doesn't think so. You been to one of his parties?
I do because we've been given forewarning for the apartment complex.
What, that you can't go to parties?
Partying,
Really?
loud music, everything.
Oh, the apartment. Are you living in this apartment complex?
No.
Oh, you can't have parties because of that. Or you're saying your parties are boring because of that.
We're not partying because we got four notices from the.
Oh, you were partying, but you got in trouble. So your parties are good parties.
Yeah, they are.
Yeah, I get it. I get it. There's evidence of. Have you gotten warnings from your landlord?
Once.
Oh, you have.
Yeah.
Was it a warning for too loud of noise,
Yes.
or was it like an awkward smell?
Actually, when I was moving to the new address,
Okay.
I keep moving till 10:05, and I see the cops because I got 5 minutes after 10.
Oh, so it wasn't even a party. You were moving.
Yeah, I was moving.
You were moving too loudly.
Yeah, moving, and I was 10.
Yeah, you're a
5
risk.
minutes.
You're a risk taker. So it makes you feel better. I don't party either. Even in college, I never partied.
Okay.
When I was an undergrad, I was sitting there writing software and stuff like that. All my buddies were out at the bars. That's probably why I have a PhD and they don't. Yeah, I'm also working until 10 o'clock at night tonight. So, That's where that PhD got me. All right. Well, at least this is a fun group, right? Well, except you. All right. So in any case, new keyword always returns a memory address. Always, 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 always. So AR is built in terms of the new keyword because this is the value. Everything over here is the value returned. So on the right-hand side of this assignment operator is the value that gets returned and stored in AR. Since the new keyword's involved, the value will always be a memory address, so AR holds a memory address, not an array. That memory address points into memory where our array lives. Okay? Make sense?
So in this case, when we print AR, it will put us on this. That's why.
Yeah, that's why. So, yep, exactly. So if we come up here and I say system.out.println AR, and I say system.out.println the chars, this will print out the memory address where this array lives. This will print out the memory address where this array lives. Did I print two things? Oh, it's actually interesting. Just pretend like you didn't see this for a second. So I don't want to have to explain this yet. So now two things show up, right? Okay. I'll give you some foreshadowing. Strings are implemented as character arrays. Strings are implemented as character arrays. A string is a collection of chars. So under the hood, the person who wrote strings wrote it as a character array. So when I created a char array, this guy functionally is the empty string.
Oh, so it prints the value.
It printed right here.
Value is
It's the empty string. Okay? But that's not related to our lesson that we're talking about right now. We're talking about arrays. It prints out memory addresses. So just roll with me that this was actually a float array that I inappropriately named the chars. Okay? As opposed to system.out.println treating it as a string. Okay? And actually the reason it showed the empty string isn't because strings are implemented as char arrays. It's because there's a version of println that knows how to print a char array. Let me show you that real quick. Having to show way too many magic tricks. Java.sun.com. And this is why we never get out before 10. This is on you. Okay. It's actually an important thing to understand. This is the kind of stuff I like explaining. So I'll go into actually it's print writer. Well, this is java.lang. We'll go to system dot out. It's print stream. So here's our println methods inside print stream. So first of all, class method or instance method?
Doesn't say static.
Doesn't say static, which means what? Instance method. No static, must be an instance method. How do I call instance methods? Using an instance of the class in which the method was defined. So this guy was defined inside of the print stream class, and I have an instance of that class called system.out. Don't worry about that too much. We haven't followed it too much, but I promise you system.out is in fact an instance of the print stream class. That's why we say system.out.println. We're calling the out variable, which is an instance of print stream. We're calling his instance method called println. And there's a whole bunch of versions of this method. What's it called when we have more than one method with the same name but a different number and or type of parameters? Polymorphism. So notice that we have a whole bunch of println methods here. This one takes nothing. This one takes a Boolean. This one takes a char. This one takes a char array. And the char array version of this guy prints the array of characters, and then terminates the line. So it prints it as if it was a string. That's why we didn't get the memory address. All right? Then we have one that takes in a double. We have one that takes in a float, an int, a long. We have another one that takes in a string. And then we have one that takes in an object. Now, to support your question from before, in terms of Java, Java believes arrays are objects. Because when I call the println method, passing it my integer array, AR, it's calling that version of it. Okay? It's calling that version of it. So it's treating an array as a generic object. And later on, it'll make some sense as to why it prints out the memory address thing. It has to do with the toString method and stuff like that. But I don't want to get too far off our course here.
So the new keyword is actually creating an object, right?
New keyword finds memory addresses.
So it's not creating an object.
No. New keyword finds a memory address. Now, you will find this out, though. Every single time an object is being created, the new keyword will be present. Okay? The new keyword does not create an object. The new keyword only finds the memory for where an object will be built. Something else actually creates the object, and that's called a constructor. Okay? But the new keyword will always be present when a new object's being created. Okay? Not that important for us right now, since that's kind of next week when we start talking about objects. But pretty much whenever we create anything that's not a primitive type, the new keyword will be present, unless it's a string. And then with strings, the new keyword could be present if we chose. All right? Similarly, strings are objects, right? But so when I say println, it doesn't call that version of println. It calls this version of println, the one that takes a string as a parameter. Okay, so there's a whole bunch of versions of println inside of the printstream class. One for every different situation with the catch-all of the object. So, well, we know how to print all the primitive types individually. We know how to print char arrays. So if you pass me one of those, I'm not going to print a memory address for you, make you look stupid. If you pass me a string, I'll print that out to look nice. Anything else falls underneath the object category, and we will do whatever that object says we should do. So by default, objects will just print out their memory address. And there's a reason for that, and I'll explain it when we talk about objects. All right, so that's why our char array didn't give us an address. It's because there's a special version of println for that guy. Okay. All right. So in any case, new keyword always returns a memory address. That memory address is what gets stored inside of AR. It is said that that memory address points into real memory where the actual value of our array lives. We could call this guy over here the constructor. This is the guy, by your question, who actually builds the array. The new keyword finds the plot of land. This guy actually constructs the array at that plot of land. Okay? But we wouldn't call this guy a constructor yet. When we talk about constructor is a term used specifically with objects that we write and objects that we use. Arrays are like that fakesy object. Okay? So I don't want to use the word constructor at this point because I don't really want us to think about arrays as objects because it's kind of it sits in the middle somewhere. Okay? And that'll make some sense when I talk about some of the objects that are in existence that allow us to do stuff to arrays. All right, so in any case, this guy built it. This guy created the memory, found the memory for us to build it. So this array gets built up in memory by this dude. This variable holds the value that points to that guy in memory. All right, now syntax. For putting stuff into an array, let's just go back to my integer array here. If I want to store at bucket 0 of my integer array the number 5, I say that. If I want to print the value at bucket 0, I say that. Okay, so arrays are read-write. So we can put something into a bucket of an array using the assignment operator by putting this syntax to the left of the assignment operator and the value we'd like to store there to the right. Okay, so this is storing the value 5 in bucket 0 of this array. And I'm going to explain what this syntax over here means in a second. But for right now, we can think of this kind of like being char at of a string. Okay, but it's important to note that strings are read-only. Char at is a one-way street. So if I have a string hello, so for instance, I have string s is equal to hello, s.char at 0 will give me the h. But I can't say change that to a b. Okay? First of all, this boils down to a character, so what actually this is saying is change h to a b, which doesn't make any sense. Right? But even if it could work that way, this is a one-way street. This extracts a value, gives us a copy of the value that's in a string, but we have no way of overwriting a character in a string. We have to build a brand new string. Okay? For those of you who think I'm lying, who cheated and used string buffer, what do you think string buffer does? Builds a brand new string. That's what it does. Builds a string. So fine, there's a class called string buffer that allow you to change the value in a particular bucket in a string. All it's doing in the background is building you a brand new string. Okay, so it's still being inefficient, it's just hiding it from you. All right, so strings are a one-way street. We use concatenation to add on to a string. But we can't change something that's in a string once it's there without building a brand new one. Make sense? So strings are read-only. Arrays, though, are read-write. So I create the array right here. I'm going to write the value 5 to bucket 0 of the array right there. I'm going to read whatever's at bucket 0 of the array right there. Okay? So arrays can be on either side of the assignment operator. Like I can say int b is equal to AR at bucket 0. I will read the value out of the array at bucket 0. This will boil down to the int that lives at bucket 0, and I'll store that value into b. Okay? Make sense? Important concept, arrays are read-write. Now, what does this syntax mean? AR at bucket 0, or AR at bucket 1, or AR at bucket 2. We see up here that bucket 0 of this array is at memory address 100. Bucket 3 of this array is at memory address 106. This is based on my sample where I've said the memory address where this guy lives is memory address 100 to make the math easy. Okay? So in this particular case, the new keyword returned memory address 100, and then the constructor built that array starting at memory address 100. So when I say AR at bucket 0, this actually translates into this. AR plus 0 times size of, in this case an integer, because this is an array of ints. Okay, it actually translates into that. Well, what's the current value of AR? 100 plus 0 times, what's the size of an integer in bytes? 32 bits, 2 bytes. 2 bytes. Or I'm sorry, 4 bytes. And actually, I wrote this wrong. I did this for chars. So it serves me right for creating 2 different arrays. So a int is 4 bytes big. So we jump 100, 104, 108, 112, 116. So 0 times size of int, which is, so 0 times 4 is the size of an integer, 4 bytes. So 100 plus 0 times 4 is 100. Here's the value at memory address 100, which is also the value at bucket 0. Bucket 3, AR plus 3 times size event. 100 plus 3 times 4, which is 112. So the value at memory address 112 is the value at bucket 3 of the array. That is why arrays have to be contiguous in memory. They have to be contiguous in memory because when we go to a particular bucket of an array, it is calculatable. So we can calculate the exact memory address we need to go to just by looking at what bucket we want to access. So this says go to the base address of AR, that is the address stored inside of the pointer AR, then travel 3 times the size of the kind of value we're storing. And that will take you to the actual place where that value lives in memory. So this maps between a bucket position and an actual memory address. That make sense? Okay. Now an important thing here is that arrays, let's throw another little line in here under arrays, are considered to be very fast, as in high performance. Arrays are considered to be memory inefficient. All right, so those are the trade-offs. They're high performance, but they're memory inefficient. And I'll tell you why at the high level, and then we'll actually experience it. So let's say you've hired that real estate agent to build your house. Okay? Well, to get you the plot of land for your house. Then you hire the contractor, the constructor, who's going to go and build your actual house. So you have your house. And so you got your 3,000 square foot ranch. Beautiful place. You decide, you know what? I'd like to add a porch in the backyard. Right? No big deal. Any of you handy? Could you build a porch? Can't build a porch? None of you? You can't get some of your party buddies to... So, we're going to build a porch. Now, normal people, what do? Well, if you're handy, you go and build the porch yourself. Or if you're not, you hire somebody to come and add a porch onto your house. Not with arrays. What we're going to do is we're going to burn this house down. Okay? We're going to hire a real estate agent. They're going to go find us a new plot of land. Big enough to build our original house plus a porch. And then we're going to rebuild the house and add the porch while we're rebuilding it. Okay? Is that efficient? In real life, might you think twice about adding a porch to your house if you had to burn your house down in order to do it?
If you have insurance.
Get the insurance to cover it, right? I got replacement value.
With the Porsche.
That's right. I had a Porsche. It was in the garage. You were driving a Vespa that somebody spray painted Porsche on it. All right. So in any case, it's memory inefficient for that reason. Once you build an array, it is a fixed structure. We cannot add to it. We cannot subtract from it. If it started off with 10 containers, or in our case here 5, that's how many it has. It's capable of holding 5 integers. We don't have to fill it. We can choose to put 1 or 2 integers in there if we'd like. We don't have to use all 5 buckets. But we don't get a 6th bucket. Make sense? We don't get a 7th bucket. If you buy a container from Target with 5 buckets in it for holding shoes, and you buy a 6th pair of shoes, well, you either get rid of one of your old pairs of shoes, so you only ever have to store 5, or you throw that container out, go back to Target and buy a new one that has 6 containers in it. That make sense?
But what about if we don't know the size of the array? How much will it be? Depends on the inputs.
Excellent question. So the idea is here, well, if I'm going to build a structure for storing a bunch of values, remember, arrays are a collection of like data stored contiguously in memory. That's what an array is. Okay, that's the kind of animal it is. And you're saying, well, I know I need to store a bunch of numbers, but how many numbers do I have to store? Okay? Well, if you're going to use an array, a couple things are possible. One, you can say, well, I'm going to store, I know I need to store exactly 5 numbers. Array is the perfect solution for that. Okay? I need 5 numbers, never going to be more, never going to be less. Create my array for 5. Now I have something that is the perfect size and fast at the same time. That array is not memory inefficient. It's the perfect size of memory, right? Okay. But what if you know, well, I'm going to need to store at least 5 things, but maybe as much as 1,000. Okay. Well, so now you're going to say, well, as far as what's in my toolbox right now, my only option for storing more than one value under a single variable name is an array. So I'm still going to go with the array, but now I got to come back and say, okay, well, I need to store at least 5 things. So it needs to be at least size 5. But it might end up holding as many as 1,000 things. So you might decide, well, let's just go ahead and make it so it's capable of holding 1,000. You'll only be using 5 for the time being. So just like you go shopping at Target, you buy that organizer, and you only have 5 pairs of shoes, but you buy the, well, I don't know if they sell these, but you buy the one that has 1,000 little cubby holes to allow you to grow into it, right? Okay, so it's that type of thing. It becomes memory inefficient. You got this giant organizer in your closet now for holding 1,000 pairs of shoes, and you only have 5 pairs of shoes in there. That make sense? Okay. Yeah, we have a little shoe bench at our house when you first walk in. My wife only allows me to have 2 pairs of shoes out at once. So like the shoes I wear to work every day, and then I also have my Crocs that I use to like scamper around the house. Because she doesn't let me wear my shoes in the house, like get footprints everywhere. But she's got like a whole bunch of pairs of shoes there. And the thing is, we have the shoe bench, but my shoes don't really fit in it. I have what she refers to as Flintstone feet. Those shoe benches are not made for size 15 shoes. See, the whole world procrastinates, not against fat people, but also just big people. You don't have to be fat to have big feet, do you? It's just garbage. In fact, there was this one time I was in a taxi cab in New York City. I had trouble getting out of it. I was in the back seat of a Prius. That was it. Yeah, Prius, little tiny car. And the thing is, I'm a realist. See, my wife always thinks about these what ifs. Like, yeah, it's not going to be easy for me to get into the back seat of a Prius, but once I'm in, let's just get where we're going. You know, the guy tried to like wave us off and says, "You're not going to fit in my car." No, I think we can make it. Okay, so I squeeze into this Prius. I have to climb in head first, kind of like putting it on like a shirt, right? My wife drives a Honda Civic, and she says that's too big for her. She drives this little tiny car. So when I have to get into it, I crawl in head first, and I kind of flip myself over. But getting out's actually easier. So I can get out as long as the headroom's high enough. I'm weirdly tall. Torso up, I'm about 6'8". But in real life, I'm only about 6'4". I have short legs. My legs are only like 30.5 inches.
What do you drive?
Huh?
What do you drive?
I drive a SUV, a Flex, a bigger car. I had an Expedition before that, so I drive big vehicles. But in any case, so I got into this Prius. Getting out had nothing to do with fatness. Okay? I could not get my shoes turned. I would have had to break my ankles to get out of this thing. Okay? So I ended up, while the guy was getting the suitcase and stuff out of the back, we were at our hotel, I ended up just dumping myself out into the street. So I'm sitting in there, I just lean backwards and there's this fall. Yeah, that's pretty funny. Seemed like it was the easiest solution. I'm a problem solver, right? It was that or remove the front seats. Those were our options.
I'll rent it in Palm next time.
No, this was a taxi. I would never rent a Prius. Okay, this was a one-time thing. I wouldn't get in and out of this thing for the whole trip. Okay. Okay, that's when you go and you Photoshop the coupon that says you get 2 upgrades to an enterprise rent-a-car.
Can you do that?
Well,
Oh wait, wait,
yeah, as long as I've had a promotion at some point where, you know,
have a barcode.
Huh?
Scan.
the guy never takes the coupon. I just show him on my phone. I show him my little photoshopped picture of my coupon that says I get 2 class upgrades.
You can do that.
And then we get out there and I talk him into even a bigger one. It's like, oh, I don't know if all my awesomeness is going to fit in that. Next thing you know, I'm driving out of there in a van.
Thanks for the soft copy versions. Yeah.
See, I paid for a compact left in a van. Or I get SUVs most of the time. I pay for like the smallest little car.
You gotta go with
Yeah, can I use both of these coupons together? I forged both of them. Do you mind? Is that cool? Don't do any of that. We have an ethical computing course. I don't teach it.
I'm done with it, so. You can do it now.
All right, so in any case, arrays are fast but memory inefficient. And for those of you who are planning on going on to the second course, the 537 class, 837 if you do the online, it continues on where this class leaves off, and you were asking about it during break. It's our data structures course. And that course starts off with the concept of something called a linked list. The linked list is the antithesis to the array. They're slow, but very memory efficient. And they solve that problem of how many things do I need to store. You start off with an empty list, and then as you need to store stuff, you add 1 bucket at a time, and you don't have to burn the house down. Okay? But the trade-off is you can't calculate. You can't just jump to bucket 3. Because when you were building those elements of the linked list, they aren't necessarily right next to each other in memory.
And you can't delete it from the middle also, right?
You can't change an array at all.
Yeah.
Array is structurally done after you build it. Linked lists, which we're not talking about right now, are very malleable. You can change linked lists to your heart's content. Add stuff, remove stuff, whatever you want. But it's slow to go through them because you can't calculate the position of the buckets because they're not right next to each other in memory. Okay? So the array's strengths are directly linked to the array's weaknesses. It's fast because I can run through an array without actually having to start at this bucket, then go to this bucket, then go to this bucket. I can just jump to the bucket I want to get to using this math right here. Does that make sense? Fast. Okay? But you better make them big enough to start with. You think you might want a porch, build the porch when you first build the house. All right? Make sense? Okay, so that's the concept of an array. Syntax builds one like this. We can fill it up. Here, let's just fill one real quick here. So we'll say for int I is equal to 0, I is less than, how many elements are in AR? AR dot length. And this is a field. It's not a method. We know it's not a method because it doesn't have the opening and closing parentheses on it. Okay, so I is less than AR.length, I plus plus, and we'll say AR is AR at bucket I is equal to I plus 1. So we'll fill it up 1, 2, 3, 4, 5. Bucket 0 will be a 1, that kind of stuff. All right. Now let's write a method. So we're going to write a method, static void print array, and this guy will take an int array as a parameter. We'll call it AR again. And this guy's going to say for int I is equal to 0, I is less than AR.length, I plus plus, system.out.println AR at bucket I. Okay. Class method or instance method? How do you know? Static. How do you call class methods? Name of the class was the method was defined. Name of this class is driver. So I'll say driver dot print array. This guy takes an integer array as a parameter. The integer array I'll pass him is AR. And he's going to go ahead and display the contents of that array. So I created the array right here, which is an empty array. It's like I just went to Target, bought the shoe organizer. No shoes in it yet. Then fill it up with shoes. Put some numbers in there. Then pass that array to my print array and have it display the contents. Make sense? So this is going to print out 1, 2, 3, 4, 5. Because the contents of my array are bucket 0 is going to be 1. Bucket 1 will be 2, so on and so forth. So there's 1, 2, 3, 4, 5. Make sense?
What about if the length is 1,000 and we only got 4 items? Will I have to go by all of them?
Oh, okay, I get what you're saying. So what if it's 1,000 like this,
Yeah.
but we say let's just go to 5? We build it enough to hold 1,000, but we're actually going to only fill the first 5 buckets.
Even in printing, I mean, he said, when you're going to send the A to the print, he said A dot length, that means...
Well, yeah, so this is going to do all 1,000 buckets.
All 1,000.
Okay, but I only filled the first 5. Okay, so, and actually here, let's just make it 10, just so it doesn't scroll off the screen and we can actually see what happens. We're going to see the default value that it puts in a empty array. So we'll see a bunch of zeros. We'll see 1, 2, 3, 4, 5, and then 5 zeros. So I filled the first 5 buckets up, but here is the default value for the other 5. Now, important thing, and I've mentioned this before, but this is a good example. Never, never, never rely on default values. It's horrible programming practice. Just because you see that there's zeros in there shouldn't mean that you should ever count on there being zeros in there. If you want to count on there being zeros in the array, fill it up with zeros yourself. Don't just assume they'll be there. Okay? Depending on the compiler you're using, the default values could change. Now, realistically, they will likely always be zeros by default. Realistically. What I'm telling you is from a good programming practice perspective, never assume that a variable holds a value that you did not put there. Make sense? If you want your array to be initialized with a bunch of zeros, you fill it with zeros. Okay? Don't just rely on the fact that it already has zeros in it. Okay? Very important stuff. More important, I would say, in older languages, C and C++, where you had a lot of different compilers. This is a real problem in old C languages because you might have 30 or 40 different C compilers, and each one might treat the language a little bit differently. Maybe one of them has a default value of -1. Maybe another one has a default value of 0. Some of the most popular C compilers in the early days, just the CC compiler, C compiler, it actually, when it initialized the memory, the default values were whatever used to be there. It didn't do anything to it. Because, you know, as you, and this is something we were talking about during break, with allocating and deallocating memory. Okay? So in the early days, you had to say, I want to create enough memory for 100 of these. And later on, you would deallocate it, which basically said, I'm no longer using this chunk of memory. That chunk of memory is now available. But you know what? The crap you left behind is still there. Okay? It's still in memory. You didn't clean it up. You just said, I'm no longer using it. Okay? It's kind of like when you were moving out of your apartment. You left the garbage behind, right? Because you didn't have enough time to clean it up.
I left in the dorm rooms.
Huh?
I left in the dorm.
Oh, you do?
I got a big email from Reslife. Cleaner, we're gonna find you for that.
Seriously.
I forgot it. I was supposed to take it out. You couldn't have it.
And when I was an undergrad, I lived in the dorms. I had in my dorm room, I had 2 55-gallon fish tanks, and in one of them I had Oscars, 2 big Oscars, and in the other one I had 5 turtles. Yeah.
How did you feed them so many?
Well, that's actually interesting. So the better question is, how do you feed them during break? That's the better question. Okay, so I read that you could just cut up potatoes and throw it in there, and they'll eat it. And oh, the Oscars did beautifully. The Oscars are fish, they're kind of big fish. And so you came back. Oh, they didn't like the skin though. So you came back. You just had the potato skin floating in there, but all the potato was gone. They had ate it. They had eaten it. Apparently, I find out the turtles don't know how to control their appetite, so they just ate it all the first day. No, but they went to the bathroom a lot. So I come back, get off the elevator. I was the first dorm right off the 5th floor of the elevator. There's incense burning down the hall. Okay, and no incense allowed. First of all, that was like one of the primary rules: is no incense. Dorm director comes by, looks in. I mean, the room just reeks. Okay, dorm director comes by, sees the incense burning, and says, "You got to get some more of this burn." So I ended up getting rid of these fish tanks. I gave them away and stuff, but it was probably a month before that room was inhabitable. The smell was in the paint. Okay, so I had to get like the baking soda stuff. I just cut. It looked like it was a sandbox. I dumped this stuff all over the floor in there to absorb the odor. And then I slept down in my girlfriend, she's my wife now, but down in my girlfriend's room for like a month while this room was like detoxing. It was, how did I even get on that? What were we talking about? Oh, yeah. Yeah, cleaning your dorm room, right. I didn't get fined. I probably left that room. That room was cleaner than it had ever been. I did wall-to-wall baking soda. All right. So, in any case, here's our array. Regardless of how big it is, don't assume the default values. So I would say always make the array the correct size, or if you're going to make it 1,000, go through, fill it up with what you want your default values to be, then fill it up with your actual values, and maybe also then keep track of how many things you've actually put in there. Okay? So I have 1,000 buckets. I've only actually stored 5. So maybe you have number of records or num shoes. Okay? So you have 1,000 buckets for shoes. That's ar.length. But the number of shoes I actually have in there is num shoes. Just create another variable to keep track of how much you've actually used. All right, and we'll see some examples of that. I would say not too important for us right now. All right, so this print array works for a generic integer array. I can pass any integer array to this guy, and he will go through and print out every value in that array. So here's my array AR, and I'm going to go ahead and I'm going to create another array right after this. Int array AR2 is equal to a new integer array, and let's say that one's 1,000. And we're going to fill this guy up with random numbers. So I'll show you how to generate random numbers here real quick. So we have a class called random. And random lives in java.util. So if you highlight over this, it's going to say I need to import something else. Remember that, we saw this last time with string tokenizer. Okay, so random lives in the util library. And then I'll say for int I is equal to 0, I is less than, how many elements are in AR2? AR2.length, I plus plus. And we're going to say AR2 at bucket I gets r dot nextInt. What's this guy screwed about? Oh, I didn't write a Boolean expression. There we go. Okay, now r.nextInt. There's actually 2 versions of the nextInt method. And here, I'll even show it to you in the documentation since we have it pulled up. So I'll go to java.util. Oh, hold on. Well, it comes after that. I gotta learn my ABCs. It's a problem. Oh, that's JavaX. That's why it's not showing up. Where's Java dot? There we go. And we have a class in here called random. And we scroll down here and we see that, don't worry about the constructor thing. We'll talk about that next class. But we're going to see that we have some methods in here. And one of the methods is called nextInt. Class method or instance method? Instance method. How do you know? No static. Okay, so how do we call it? We call it using an instance of the class in which it was defined. What class was this defined in? The random class. So I created an instance of the random class right here. And I'm calling the nextInt method using that instance. Make sense? The nextInt method, this version of it, returns a random number in the range of all integers. That means negative 2 billion to positive 2 billion. Okay? So roll the dice. I will give you some integer in the range of all the integers. Fair enough? All right. So we also see there's a second version of this method. What's it called when we have more than one method with the same name with a different number and or type of parameters? Polymorphism. So here's two methods, both called nextInt. One takes no parameters, the other one takes an integer. Okay? This one returns a random integer in the range of 0 to n minus 1, not including n. So if I say r.nextInt 10, I will get numbers between 0 and 9. Okay? So this is a convenient way for getting positive numbers in a certain range. Okay, but as I have it written right now, I'm just filling this guy up with random integers. And then we'll call driver.printArray, and we'll pass this guy AR2. So we should get our 1 through 5 first. We'll never see it because we're going to have 1,000 random numbers printed out after that. But trust me, this will print out 1 through 5, and then it'll print out 1,000 random integers. Okay? So there's my 1,000 random integers. Oh, see, you don't have to trust me. It's there. I would never lie to you. All right, so that's my first array. And then my second call printed out 1,000 integers in the range of all integers. So see, some of them are negative, some of them are positive, but all of them will be between negative 2 billion and positive 2 billion. Range of integers. All right, so this single method is capable of printing out any integer array. All right, so that's a good use of a method. It's a reusable chunk of code that we can call multiple times. Wrote it once, I can call it every single time I need to print out the contents of this integer array, of any integer array. All right, now we mentioned, so let's go back to just our 5-bucket array. We were talking earlier about pass by value versus pass by address, right? So right here I have an array, 5 buckets, filled it up with 1 through 5, printed out. No harm, no foul, there's my 1 through 5. Now I'm going to create an array, static void, change something. It's going to take an integer array as a parameter, and I'm going to say AR at bucket 0 is equal to, kind of taken, oh, no, this would be fine, negative 10. I was thinking we were still dealing with the random numbers. All right, so this guy's going to take an integer array as a parameter, and we're going to just change whatever's at bucket 0 to be negative 10. Fair enough? Class method or instance method? How do you know? Static. How do we call class methods? Name of the class in which the method was defined. Driver dot change something. I'll pass it AR. And I'll say driver dot print array. Pass it AR. So I'm going to define it, fill it with 1 through 5, print it. It'll print out 1 through 5. Then I'm going to pass it to this useless method called change something. And what this guy's going to do is no matter what you pass me, I'm going to change bucket 0 to be -10. I don't return anything though. Then I'll print out the contents of the array. Except this time it won't be 1 through 5. It'll be -10, 2, 3, 4, 5. 1, 2, 3, 4, 5, -10, 2, 3, 4, 5. Pass by address. Okay, and let me show you what happened there. So we filled this guy up with 1, 2, 3, 4, 5. Contents of the array, right? That's what our loop did. First line creates the bucket, loop filled it up. All right, now I have my little method down here. What I call it, change something. This guy took in an integer array, called whatever, and did some stuff. When I called change something from main, let's actually the easiest thing here real quick would be just for me to prove this to you. System.out.println AR. System.out.println AR. And then let's not call print array real quick, just so things don't get muddied. I defined my array. I filled it up with some crap. Not even important in this. It didn't even matter if I filled it. Now I'm going to print out AR. What's going to display? Memory address. AR is a pointer. AR is a variable that holds a memory address which points to where that array is. So this line right here will print out the memory address of this array, correct? Then I'm calling change something, and I'm passing it AR. Inside of change something, sure, I'm still changing it, whatever, no big deal, but I'm also printing out the memory address of this guy. Now, just to show you there's no link, I'll rename this guy Elephant. So since I changed his name here, I need to change his name here. Okay, so this AR had nothing to do with this AR. They just happen to share the same name. They're in different scopes. Remember we talked about variable scopes? Okay, so I defined AR right here. The new keyword gave me a memory address, stored the memory address in AR. I'm printing out that memory address right here. Then I'm calling change something. Change something is going to take in an integer array as a parameter. I'm going to pass it AR. AR is going to come in as a local variable called elephant, and I'm going to print out the value of elephant. I need to change this AR to, oh, here, just let me rename it to elephant. And what we're going to see is this memory address and this memory address are the same. They both point to the same place in memory. So when I made a change to elephant at bucket 0, I was making a change to this same structure, AR at bucket 0, because I was changing it in real memory. And we'll see. The output of this will be the same memory address twice. This is AR's memory address. This was elephant's memory address. So this is proof that when we called the change something method and we passed it AR sent in itself as an address rather than a copy of itself. If it was a copy, this would have been a different memory address. But in this case, it's the same memory address. So any changes we make have global impacts. When I go to elephant, so in this example here, we have another variable called elephant, which was the local variable inside the method. Elephant holds the same memory address as AR, so they both point to the same place in memory. So anything I do to elephant, elephant at bucket 0 says go to memory address 100, change the value there to -10, which is the exact same place that AR is still pointing to. That make sense? That's an example of pass by address. Now, from a programmer's perspective in Java, we are not responsible for choosing. This is more knowledge for us. Whenever you're passing an array to a method, you are passing that array by address in Java. So that means things that you do to that array inside of that method will have permanent ramifications. There's a side effect, because anything you're doing to that array inside that method will globally affect the array up in memory. As opposed to our example earlier where I had a method where I passed in an int, and we changed the int, and then we saw the original int wasn't affected. That was passed by value. I passed a copy of it rather than the original. Make sense? All right. So that is how arrays work in general. Now that we have that tool, let's see, how do I want to? I'm going to look at your assignment real quick and make sure you have everything you're going to need. So isn't this handy? Chrome remembers your password, so you only have to guess at the username. Oh, we didn't remember that either.
Pull out all the passwords at one time.
Yeah, but isn't that like stupid? That it fills in the password and I have to guess at the username?
Opposite way. There's a time to just the username.
All right. Let's see. Write a Java method that adds two fractions together and returns the result in reduced form. A fraction should be represented as a two-bucket integer array. Okay, so let me talk about that for a few minutes. And we actually probably will get out a little early. Look at that. Powered through stuff. All right, so now that you have this ability to store collections of things, now we can start utilizing this ability. And what I mean by that is I can create an integer array named a fraction. And I can say a fraction is a new integer array of size 2. And then I could say a fraction at bucket 0 is equal to 1. A fraction at bucket 1 is equal to 2. And we might say that that is the fraction 1/2. That's my representation of the fraction 1/2. A two-bucket integer array where bucket 0 is the numerator and bucket 1 is the denominator. Make sense? And I could even write a little helper method here. I can say static void display, and this is going to take in an integer array fraction. And maybe this guy just prints out system.out.println. Fraction at bucket 0 concatenated with a slash concatenated with fraction at bucket 1. So now this guy knows how to print fractions out in some sort of nice format. So I can say driver.display, pass it a fraction, and this will print out 1/2 to the screen in kind of a pretty format. That makes sense? Okay, so I've chosen to use my new tool in my toolbox, this idea of a fraction. I've chosen to represent, or I'm sorry, this idea of an array. I've chosen to represent fractions as two-bucket arrays, two-bucket integer arrays, where bucket 0 is the numerator, bucket 1 is the denominator. Make sense? Okay, so I am now taking, this is like going to Target, buying a container for something it wasn't originally meant for, and then repurposing it for something that's convenient for you. Make sense? Okay, so that's what I've done. An array was originally designed, when it was originally designed, it didn't have fractions in mind. But I decided, you know what? What's a fraction? A fraction is a numerator and a denominator. I need to be able to hold those two pieces of information. So, do I have a tool in my toolbox that allows me to hold two pieces of information associated with a single variable name? Sure, that's an array. So I'll go ahead and I'll choose to store at bucket 0 the numerator, and I'll choose to store at bucket 1 the denominator. I need to remember that. I need to remember I put my numerators at bucket 0 and my denominators at bucket 1. I didn't flip-flop them, because then things are going to go south quick, right? Okay, didn't flip-flop them. So I'm choosing to use my newfound array to solve the problem of fractions. Make sense? So this is how it wants you to represent fractions. Now I'm going to show you a little shortcut here with arrays. I'll go ahead and define another array here. I can say int array, another fraction, is equal to 1/4. And we'll see this prints out 1/4 and 1/2. So in this case, I defined a fraction. So this is like going to Target, buying a 2-bucket container with nothing in it. Then I put something in bucket 0. Then I put something in bucket 1. Then I called my display method. In this case, I'm saying create a variable of type called another fraction of type integer array and store in it these values. So similar to how strings work, this is syntactic sugar for quickly creating an array with some contents in it. So this will create a 2-bucket array where bucket 0 is a 1 and bucket 1 is a 4. That make sense? So this one line, here, we'll change this to 1/2 for right now. This one line is functionally equivalent to those 3 lines. Make sense? Now that doesn't mean always define arrays this way. In fact, you should only define arrays this way if you know what the contents of the array is going to be to begin with. If you need to store 5 numbers and you know what 5 numbers they are, you can go ahead and build the array and put the 5 numbers in there, right? Sure, no problem. If you don't know what the 5 numbers are, don't guess. Now what you could do though is if you wanted to make sure that the empty spots were zeros, you could say I'm going to create 5 numbers like that. And there's actually some classes, we won't look at them today, but there's some classes, actually let me just look quick. Yeah, I'll just show it to you real quick. Since I've made a big deal about the, so I'm going to create an integer array AR2 is equal to a new integer array of size 1000. So this is back to your example of if the most number of things I need to hold is 1000, but I only have 5 things to hold right now, and I've told you don't trust that the default value will be 0. So you could just write your own method. You could say, or your own loop for int I is equal to 0, I is less than AR2.length, I plus plus, AR2 at bucket I is equal to 0. That'll go through and that will guarantee that it's filled up with zeros, rather than you relying on the default value to be 0. Make sense? So I've explicitly filled it with zeros. Instead of writing a loop like this, there's a class built into Java. And it's in java.lang, and it's called arrays. Oh. Is it in java.lang? Or is it in util? It's in util, java.util. It's called arrays. And one of the things it has, besides the searching stuff, which I'm officially not telling you about searching stuff right now, because we're going to be dealing with that next time. We have something called fill. And fill can take an integer array. See, there's a whole bunch of different versions of fill. So polymorphism again. Fill, or one of the versions, takes in an integer array as well as the value, and it will fill up that array with that value. So I can just say, and notice that, is this a class method or an instance method? Class method, because it has static, right? How do we call class methods?
Class name.
Using the name of the class in which the method was defined. What's the name of this class? Arrays. So what I would do here is I would say, instead of this for loop I would write on my own, I would say arrays dot fill AR2 and 0. And it's going to say I need to import java.util to have access to that arrays. All right, so now that will fill up my fraction with a bunch of zeros. Make sense? Now, even though this is completely unnecessary in terms of how Java actually works, because it will automatically be filled up with zeros, this is better programming practice. Don't trust default values. Okay? And if anybody ever tries to tell you, oh, the value will just already be that, try to reprimand them. If they don't listen to them, don't trust that person again. It's bound to burn them at some point. Okay? Because one of our jobs as IT professionals is going to be not just learning how to do stuff, but also minimizing our mistakes. Okay? We're only as good as our mistakes. Correct? So when you're setting up servers, you're creating new user accounts and stuff like that, anything that you can do to minimize the number of screw-ups you have is beneficial. So little things like this, just like having the opening and closing curly braces on a for loop or an if statement instead of only using it when you need it. It never hurts to have them. That's what we talked about last class. So anything you can do to minimize your number of mistakes will benefit you. And anybody who tries to take shortcuts because they know better actually know better. You're not really helping yourself. The idea of creating a for loop that has no curly braces after it because you know you don't need curly braces, that's okay. Did you really save yourself that much by not putting the curly braces? You didn't. You saved yourself 2 lines of code and possibly a whole lot of debugging headaches at some point in the future. Nobody's impressed if you save yourself 2 lines of code. And I think I mentioned in here, last class, about the Swift programming language, which is Apple's new language, that actually requires, the whole purpose of the language is to reduce the amount of stuff you type. Yet it requires opening and closing curly braces for loops and conditionals. So that's got to tell you something. All right, so this is a little trick for quickly filling up an array with some stuff. So this arrays class has stuff in it for working with arrays. You are only right now allowed to use the fill method from this. Because next class we're going to work with some sorting stuff. And I don't want you to use the built-in sort stuff yet. Okay? Because we want to keep working on algorithms. All right, so for your homework, you're going to be creating fractions. Storing them in arrays, 2-bucket arrays like this. So you can either hard code in a fraction like that if you're testing, or you can read the fraction in and you could build the array and then fill it up with 2 things. Okay, so that's how we're representing fractions in our homework assignment. As integer arrays, where bucket 0 is the numerator and bucket 1 is the denominator. That make sense? Okay, so homework assignment says, write a Java method that adds 2 fractions together. Each of those fractions is a 2-bucket integer array. Okay? And returns the result in reduced form. So 1/2 plus 1/4 is what? Well, we got to find a common denominator first, right? So you might multiply the 1/2. So if we have this, we have 1/2 plus 1/4, and we want to find a common denominator first. Maybe we multiply the 2 denominators by each other. That's 8. So now we have 4/8 plus 2/8, which is equal to 6/8. Make sense? So now we've effectively added 1/2 plus 1/4, giving us the result 6/8. But we know that that could be reduced to 3/4. So your method should return a 2-bucket integer array containing 3/4 as the result. That make sense? So do fraction addition, where your fractions are represented as integer arrays, and make sure you also reduce your resulting fraction to its lowest common terms. Make sense? All right, so that's the programming assignment. This one is less algorithmic, more working with arrays and really seeing the weakness of arrays from a data representation perspective. We're trying to force arrays into to be used for storing fractions, where we have to remember that bucket 0 held this information and bucket 1 held this information. Maybe not a big deal for arrays since we're only storing 2 things, for fractions rather. But what if I was holding 30 pieces of information about a person? First name, their last name, phone number, social security number, home address, blah, blah, blah. Whole bunch of pieces of information. And I stored like, oh, bucket 0 is their first name, bucket 1 is their last name, bucket 2 is their phone number, bucket 3 is their social security number. Was bucket 4 their home address or their work address? See where I'm going with this? Okay, so utilizing arrays for those types of things starts losing value real quick. Because now you have to start remembering where you put crap. Okay, fraction, 2 buckets, no big deal. Okay, so that's where we're going to segue next class into talking about objects. You know, how can we build a fraction object which represents fractions in even a better way than dealing with them as arrays? All right, so that's the programming assignment. The paper, 3 to 5 page paper discussing algorithm design as it relates to time complexity. So this is the reduction part of that fraction. You won't have a problem with it for what you're working on, but I'll show you the problem next class. Reducing a fraction is actually what's known as a time complexity problem. It seems like it would be so easy, but it's actually incredibly computationally difficult. Okay? Reducing a fraction is computationally difficult for a computer. Okay? And I'll show you this next time, but the paper deals with you looking into time complexity problems. So discussing algorithm design as it relates to time complexity problems, like reducing fractions without using what's called the Euclidean algorithm for greatest common divisor, versus using the not using Euclidean algorithm versus using Euclidean algorithm. When initially solving a problem, how might one detect that a solution needs extra attention with respect to an efficient algorithm versus standard solutions, where a highly efficient solution may be indistinguishable from an inefficient one? Specifically discuss the potential trade-off between an easy-to-understand inefficient solution versus a difficult-to-follow efficient solution. Is it always better to write optimal code if the end result is difficult to follow by future programmers who may maintain your code? So this is something we've already talked about in here a little bit. So it's always better to be correct first. Write code that works. All right? Secondarily, you should write code that is readable by other people. Only if you're dealing with a time complexity issue, or you're solving a problem that really relies on performance, should you go back and look at your solution and determine whether you could optimize it. Good example here, and this is where this time complexity thing comes from, is when I was an undergrad, I used to compete in these programming competitions called Top Coder. If you ever seen the movie Top Gun, it's the same thing but for programmers. And we didn't get to shoot missiles. But I used to compete in something called Top Coder. And Top Coder had, it was like you would have 3 different problems you had to solve. And when you opened up a problem, the clock started ticking. And when you submitted the solution, the programming solution for it, you would get a number of points relative to how fast you solved it. Maybe it started at 250 and you get 175 points because it took you 5 minutes to solve or something like that. So that was just submitting it to begin with. But then you had to pass system tests. Now, one of the rules for this thing was that your programs, with the tournament director guy, when he ran it through system tests, when it actually stress test your program to make sure it worked, none of your solutions could take more than 10 seconds. Okay, so your program had to run in less than 10 seconds. All right, no harm, no foul. But we can see real quick, if I just bounce back in here, I can write a real quick program. So what is this, 10 million? So there, I'm printing out hello 10 million times, and you can get your stopwatch out. This is going to take more than 10 seconds, so we just failed the test. Simple program, but takes more than 10 seconds to run because writing stuff out to the screen is expensive. Okay, so that would have failed the test. Took too long to run. But most of the programs we write, our computers are so fast that it just instantly shows the result, right? So even if you wrote it in the least efficient way versus the most efficient way, it would still seem instantaneous. But every now and then there's a problem, like greatest common divisor, like reducing a fraction in the most obvious way, where you can solve greatest common divisor. You can reduce a fraction in a way that makes sense to a human. And that result, while accurate, is incredibly time inefficient, especially as either the numerator or denominator get larger. Okay, and we'll look at this in more detail next time, but the punchline here is that when they fed system tests to our program, the maximum size of the numerator and denominator could be like, I don't know, like 10 nines in a row or something, a relatively big number. And you had to take an array of fractions, and you had to sum all of them together and produce the final result as a reduced fraction. So you write this, and it's like, oh, this is easy. No, there's nothing hard about this program. And I submitted it. Didn't really think about it being a time complexity problem. Felt good. Thought it was going to work just fine. I failed like the third system test. Didn't know why. So they show me what the result. They show you. Here's what the inputs were. Here's what your output was. And this is why you failed. So I went and plugged in those inputs and tried it myself. How long do you think it took that program to run? To show you how inefficient. 3 days. The input they gave my program that was supposed to run in less than 10 seconds took my solution 3 days to run. They got the right answer. But it was horrifically inefficient because of the nature of that one problem. And that's really what this paper is about. Because that's where I learned about it, is because of that mistake. I looked past the problem and thought it was a very simple problem. Oh, we're reducing fractions. I just have to find the greatest common value that divides this guy and this guy. How hard can that be? So I just write a loop, right? That spins through and finds one that divides both of them. Well, if those numbers are sufficiently large, and you have to do that a sufficient number of times, that starts becoming ridiculous. All right, so one of the things to consider here is whenever you're solving a problem, you really have to think about the problem you're solving and decide, might there be some inefficiency issues here? Or is this not one of those kinds of problems? That makes sense? And at the very least, if there might be, test your program under some larger data sets. Don't just test it on 1 or 2 values and say, oh, this is good. Because my program worked just fine for the things I was feeding it for test data before I submitted it. But I wasn't submitting it 250,000 fractions that were, huge numerators and denominators that actually took my program 3 days to solve. Make sense? So that's what the paper is all about, is looking into time complexity problems and understanding that they exist. Okay? Questions, comments, concerns, bribes? 1 minute early. All right, I'll see everybody next week.